Alright students, today we shall be discussing preparation of haloarenes. By haloarenes we mean when halogen is directly attached to the aromatic ring, that is the benzene ring. So there are not too many methods by which haloarenes can be prepared. Only two methods, as you can see here. One is electrophilic substitution reaction. The other one is Sen-Meyer's reaction. Electrophilic substitution reaction is not new to you. We have already done it in the class 11 syllabus in the chapter hydrocarbons. So let us just revise it. Benzene or substituted benzene. By substituted benzene we mean when there is already some other group present in the benzene ring. When treated with halogens, not all halogens, only chlorine and bromine, in the presence of a Lewis acid catalyst. Now if you remember, Lewis acid catalyst could be anhydrous aluminum chloride, it may be anhydrous BF3, it may be only iron, it may be only aluminium. Any of these reagents can be considered as Lewis acid catalyst, and very importantly the reaction has to be carried out in the dark. Okay, then the haloarenes are formed. Now if you already have a substituent in the benzene ring, then the position of the incoming halogen will be decided what is the effect of the group which is already present. Let us try to understand with examples. So you can see here we have taken benzene and we have taken chlorine as the halogen. Now since we have taken chlorine here, we have taken here anhydrous AlCl3. If I take bromine here, then we should take AlBr3. Or you can simply take only aluminium or only iron, or even FeCl3 can be taken as a Lewis acid catalyst. So what we get, chlorine gets introduced in the benzene ring in any of the positions because all the positions of benzene are equivalent here, and the product which you get is chlorobenzene. Now if you already have a substituent here, as you can see here we have taken benzene with CH3 group, and CH3 is an electron donating group. Now I asked you to go through the directive influence from class 11 book. If whenever electron donating groups are there, they increase the electron density in the ortho and para position during resonance, and that's why the electrophile being positively charged, they get introduced either in the ortho position or in the para position, and very commonly it is found that para products are the major products. Now why para products are major products? Because you see the two groups are very close to each other, so there will be a lot of electronic repulsion. As you know, each bond is made up of electrons, so the more the groups are close to each other, they will suffer electronic repulsion because electrons are like charges. However, in the para position they are quite far from each other, so experience less repulsion, hence they are more stable. Now you see the mixture of products we get here is 2-bromotoluene and 4-bromotoluene, in other words ortho-bromotoluene or para-bromotoluene. But when you have an electron withdrawing group such as here, as NO2 is written EWG, you can see here it's written EWG, nitro group pulls the electron towards itself by making the ortho and para position less electron rich. So in comparison, meta position is more electron rich. So when it undergoes halogenation reaction, you can see I have changed catalyst here in these two cases. We have taken iron, but make sure it has to be dark. Then the halogen will get introduced in the meta position. Very, very important. Okay. So that's all about preparation of haloarenes by the process called electrophilic substitution reaction, and it was not new reaction to you. We have done it in 11 as well. Now the next reaction which is new for you, that is called Sen-Meyer's reaction. It's a name reaction. Now what is Sen-Meyer's reaction? You see the starting material for Sen-Meyer's reaction is actually aniline, C6H5NH2. Now when you treat C6H5NH2 with nitrous acid, HNO2, nitrous acid is also a very, very unstable acid and it cannot be prepared beforehand. You have to prepare it in situ. How do you prepare it in situ? You prepare it in situ by treating sodium nitrite and concentrated HCl, which generates HNO2. So when you treat this aniline with nitrous acid, it forms a reaction intermediate. By reaction intermediate means you cannot isolate this product, it forms during the course of a reaction, and that reaction intermediate is called benzene diazonium chloride. In short, we call it BDC. Now this benzene diazonium chloride is a very important intermediate, because if we want to remove this NH2 from the benzene ring, this is the only possible way by which we can remove this NH2 group, by converting it to BDC. So when BDC is treated with cuprous halide, remember copper has two oxidation states, +1 and +2. +1 state is called cuprous state, +2 state is called cupric state. So here we need cuprous halide together with the halo acid. That means if you take copper cuprous chloride, then you should take HCl. If you take cuprous bromide, then you should take HBr accordingly. Then we can get haloarenes. Let's try to understand the reaction. You can see this is the structure of BDC. Why do we call it BDC or benzene diazonium chloride? Benzene because of the benzene ring. The meaning azo means nitrogen. So there are two nitrogens, so diazo. Nitrogen carrying a positive charge, so yum. So benzene diazonium, and the chloride is there to neutralize the positive charge. So that's how you should remember the formula of BDC. How we get BDC? We get BDC by treating aniline with nitrous acid. So you can see here, when aniline is treated with cuprous chloride and HCl, you can see the halogen present out here is Cl. So we get chlorobenzene. You may note the nitrogen is removed from here. And if you take cuprous bromide and HBr, then you get bromobenzene. Okay. So whenever copper salts are used together with their haloacids, the reaction name is Sandmeier's reaction. We may prepare iodobenzene as well from BDC, but the reaction is not known as Sandmeier's reaction, because the reagent used here is not cuprous salt, rather it is potassium iodide. So when BDC is heated with potassium iodide, then you get iodobenzene. So with this we come to the end of methods of preparation of haloarenes, very important reactions and very commonly asked reactions. Next we move to physical properties. Physical properties of haloalkanes and haloarenes. Okay, first of all, let's talk about their colors. They're colorless when they are pure, but as you keep them for longer time, they sometimes develop little color because of decomposition. Odor, they have sweet smell, especially aromatic ones. Melting and boiling points. As you know, melting point and boiling point, they are directly proportional to molar mass. So as the molar mass increases, melting and boiling point also increases. To understand this example, see, you have taken CH3Cl where we have only one carbon. C2H5Cl, number of carbon increased, so molar mass also increased. C3H7Cl, so we have 3 carbons now, so molar mass increased further. So their boiling point also will keep on increasing, melting point as well as boiling point. And we have taken another example where we have kept the alkyl group same, everywhere it is CH3, but we have changed the halogen, fluoro, then chloro, then bromo, then iodo. And as you know, as you go down in group 17, in every group actually the atomic mass of the elements increases. So here also the molar masses will keep on increasing because of the presence of the different halogens, and therefore the boiling points will keep on increasing. The question arises when they are isomeric in nature. I asked you to earlier also that these properties remain more or less same for all functional groups. When you have a straight chain molecule, you see this is bromobutane having a linear chain, and it will have maximum boiling point 375. You need not remember the value, but the trend you need to remember. Now when we have the same formula, same molecular formula, But you see, we have shifted the position of bromine to carbon 2. Now the boiling point decreases because boiling point decreases with branching. More and more branches are created, boiling point will keep on decreasing. Here you see we have the third example. Here also it is the same compound, but I am not the same compound, I mean same molecular formula, but here we have two branches now. Because of the two branches, the boiling point has decreased further. So for isomeric haloalkanes, you must remember, for isomeric haloalkanes, boiling point of isomeric haloalkanes decreases with branching. Very, very important. Now what happens when we have aromatic isomeric haloalkanes? You see here we have dichlorobenzene. Here it is 1,2-dichloro, here it is 1,3-dichloro, and here it is 1,4-dichloro. You see it is exercise question 10.18. Page number in my book is 312. You may check your page number. Question number is 10.18. Now why the boiling points of these isomers are different when they have same molar masses? You see the highest molar mass boiling point goes to para isomer. The highest boiling point of para isomer is due to its symmetrical structure. You see here they are considered to be branches and the molecules cannot come very close to each other. Now more is the distance between the molecules, more will be the less will be the force of attraction, so they will be having less boiling point. More is the area of contact, more will be the melting and boiling point. So because of its symmetrical structure, another molecule of dichlorobenzene can come very close to each other and the boiling point is maximum. Very important question, may be asked in the exam. Next is density. Now we know that density is mass by volume. Now it's quite clear, as the mass keeps on increasing, by keeping the volume constant, the density also will also keep on increasing. For this you can refer to table 10.3 from your textbook. Alright, solubility, very, very important. It is also exercise question 10.12 from your exercise. Haloalkanes and haloarenes, though the carbon halogen bond is polar, and we know like dissolves like, but still they are not polar, not soluble in water. Okay, now there are three reasons for this. The first reason is energy required to overcome the force of attractions is more than energy released when they form the bonds. Okay. Point number 2, to break the hydrogen bond between water molecules is much more when the new bonds are formed. Less energy is released when new attractions are set up between Rx and water. So why they are not soluble in water? First of all, the molecules are strongly held to each other, so it demands more energy. Water itself is having lot of hydrogen bonds, so to break the hydrogen bond also you require energy. But when haloalkanes form a bond with water, when they get soluble, the energy released during bond formation is much less. So it is a kind of business. When you spend some money in buying the raw materials and you sell it off, if the selling price is less than cost price, then you cannot run the business because you will not have any profit. So it is always important that the energy released should be always more than energy required. But in this present case, it is reverse. Here energy released is less compared to energy required. As a result, haloalkanes and haloarenes are not soluble in water. However, they are highly soluble in organic solvents such as carbon disulfide, carbon tetrachloride, chloroform, etc. Now I am giving you a homework. Please try to solve in-text question 10.6. In my book it is page 291. After that we shall begin with the chemical properties.